Hey, Mr. D.
How's it going, my friend?
Hey, I want to ask a question. Favorite movie? Anything pops for you?
I have a bunch, but I'll go back to my nerdy sci-fi roots, and I would say there's an old one, Back to the Future.
Oh,
I loved that movie. Kind of funny that the future date that Back to the Future goes to
is now the past. Yeah, it's now the past.
none of those things have happened. How about you?
For me, it's sort of a book movie combination. It's The Lord of the Rings. I've actually read The Lord of the Rings probably 9 times in my life, twice out loud. And when the movies came out, I was so excited, and they were awesome. I too am a geek. Okay.
Also nerd. Also nerd.
I am 100% geekdom. All right, today we're going to talk about measurement. So we talked mostly about matter at the beginning set of videos, but now we're going to talk about measurement. Get kind of mathy a little bit. So this is the importance of measurements. Mr. D, what do you want to share with us?
Let's talk about how we make observations before we actually talk about how we do measurements. Okay. And sometimes we make an observation that has a number in it, and sometimes we make an observation that doesn't have a number in it. So, for example, if we make an observation and there's a number involved, we call those quantitative. And if there's not a number involved, we call those qualitative. So if I were to say I have 7 guinea pigs, that has a number involved, that would be quantitative. If I were to say smelly boys, that would be a qualitative descriptor. Now,
so like red would be qualitative, and 32.5 grams would be quantitative. So it's a number versus not a number. And we can describe things in lots of different ways, right? But that's a good way. So one way to classify how we make observations is qualitative and quantitative. Now let's focus on quantitative, because that could be difficult for students, right, Mr. D? So tell me about this. 36 plus 16 equals 1.
Those of you are thinking, well, that's why numbers are difficult. There it is right there.
Is that true? I think 40, 52.
And if you take a look at that, you can be like, well, how is that possible, right?
It's not possible. No. Well, wait. How is it possible?
Well, how about if we did 36 weeks plus 16 weeks equals 1 year?
Oh, I see. So we got 36 weeks. I'll say WK. Now, yeah. So what matters is that you must also have like what you're measuring next to it. And folks,
I actually did this with this in class a couple years back, and a student off the cuff just said, well, what about 36 cards plus 16 cards equals 1 deck? Which speaks a little bit to probably their gambling problem, but there's more than one way to have units mean something. So we say this always, don't we, Mr. Bergman? A number by itself means what?
Nothing. So write that down. A number by itself means nothing. So what does it need? It needs this word right here we call a unit. So if you write a number, so I'll say this, never, ever, ever, never write a naked number. A naked number is a number without a unit. You might see on your papers, naked number. Don't be naked. Okay, sorry, just saying that. All right, so you must have that. So let's jot this down. You've got a unit, you've got exponent, and you got math. And this is a workflow. Sketch this, folks. Explain this now, Mr. D.
So it's really important. You might have heard of order of operation in math before, but it's really, really important that you always follow this order. So whenever you're dealing with a problem, and if there's a unit in it, you have to take care of it first. After you take care of units, you can go to exponents. After you take care of exponents, then and then only then can you actually do the math for significant figures, which we'll talk about. Now, you don't know very much about how we manipulate units or exponents and whatnot, but we are going to talk about right now about how we manipulate exponents. Just have this flow chart somewhere, because we're going to use it all the time.
So, Mr. D, next, what we want to do is we want to look here at exponents and learn a little bit about how scientists work with exponents. So, a couple of rules here. What's the first rule here? So, blank provides a way for very large and small numbers to be easily written. What's that? What should we put in there?
Scientific notation.
Scientific notation. Got it. Okay, so we're going to learn about something called scientific notation. You might have been familiar with that, but also it helps us with what else?
significant figures, which is going to be the focus on our next video.
That's our next video. Okay, good enough. All right, and then secondly, in order for scientific notation to be, need to know how to do what?
You have to be able to shift decimal places in order to be able to work with exponents.
Decimals, shifting. Okay, good, good, good. And we need two simple rules. What are the two simple rules?
It's kind of corny, but we do it this way. Lefty, largy.
Lefty. Okay, and the second one?
The word lefty means whenever you move the decimal place to the left, you make your exponent larger.
So if you move it to the left, you make your exponent larger. Okay, give me some examples. Well, let's take a look at some examples. Let's take the example of 300,000. That's a big number, right? So if I want to say lefty largy, so how would I write this in scientific notation?
Well, you use a decimal or an implied decimal. Now,
Well, there's a decimal at the end here, right? Or implied at least, right?
Yeah,
and if I want to move it to the left, I can move it 1, 2, 3, 4, 5. So how do I write that?
So you moved it 5 lefty. We have to make our exponent 5 largy. Now remember, every number has an exponent on the end of it. If I just say the number 13, it really is 13 times 10 to the 0. We don't say 13 times 10 to the 0 because that's silly. But there is a 10 to the 0 there, which means 1.
Because 10 to the 0 is to the first power, all right? But you could even write this as 1.3 times 10 to the first if I move it here. Now, we would never do that with number 13. So when we talk about this, we use the scientific notation. We have really big numbers, and actually we'll learn in a minute, really small numbers. Let's do another example. Let's say we have 930,000,000. So really big number, right? 930 million. So what would I do?
So same thing. Start where we think our decimal place is.
Here, 1, 2, 3, 4, 5, 6, 7, 8. So between the 9 and the 3, you always go to the first non-zero digit. So it'd be 9.3 times 10 to the 8th. And actually, we should make a note here. What we are doing is we're breaking a rule we just talked about. Maybe this is, kilometers, and this is meters per second, or something like that. We would have some kind of a unit there, right? And then
a great teaching mechanism there. We tell them a number by itself means nothing, and then we just leave out all the units.
Yeah. But what about this one here? 5, 4, 3, 2.1234. How would you do that one?
So here you could actually shift your decimal place in either direction, but we can start at the decimal place, an actual decimal place, and shift our way over towards the left.
So I go over 3, so this would be 5.4321234 times 10 to the, what was it, 3's place? Yeah, third. Yeah, that would be a weird one. I would just leave it this way if that was the case. But yeah. So anyways, any other ones that we think we need to do? I think that's good. So that's lefty largy. What about the other one? What's number 2?
Again, kind of silly. Righty reducey.
Righty reducey.
This is a deviation from the righty tighty lefty loosey thing, but righty reducey, which means if you move your decimal to the right, you reduce your exponent. As
a note, you're going to move it to the right when you have small numbers. These are obviously big numbers. Now we're going to work with teensy-weensy smally numbers, 0.00089. So if I've got 0.000 whatever 89, I want to move the decimal over to the right, because righty reducey, 1, 2, 3, 4. So the decimal always goes after the first non-zero digit. So that's 8.9 times 10. How many was it? 1, 2, 3, 4. Now this is tricky. Do I write 4 here?
No, and remember we said before, pretend we have a 10 to the 0 here. If we want to reduce 10 to the 0 by 4...
Oh, you subtract 4 from 0, so that's negative 4, right? Yeah. Or we take another number. Let's just do them over here. What if I've got, 0.000000004, let's just say. And this is in meters, something like the width of an atom or something like that. And, well, it's just going to be 4 times 10 to the minus some big number. 1, so 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the minus 8th meters. And let's do it the reverse, though, Mr. D. Let's do 2 different problems. Let's say I've got 4.3 times 10 to the 6th. How could I write that as a regular number? How could I go the other direction?
Well, if you're gonna reduce the number or reduce the exponent, then you're going to have to go right with the decimal if you want to.
Because I want to make it back to 10 to the 0, right, so to speak. So I want to make it so it's like a regular number. So now we're actually going to apply rule number 2, and we're going to go righty 6 places. So I'm going to say 4 and then 3, and then the first place is here. So that counts as 1, 2, 3, 4, 5, 6. And let's say this is kilometers, maybe the difference between here and the sun. All right, so that's how you would do that. But what if I take a small number? Let's say I have, let's say 4.3 again. Or I said 8, never. Times 10 to the minus 6th. And again, let's say that's in meters or something like that. How would I write that in regular exponents? And so if I want to do this, I want to move it over to the left 6 because we're going to make it largy. And so we've got 4 and 8. The first decimals to here. So that's 1, 2, 3, 4, 5, 6. And there we have it. Now, one mistake I've seen a lot of students do is they just add zeros. So they see the 6 and they go 1, 2, 3, 4, 5, and they add a 6th zero. It's not zeros, it's places as you move across. And the same thing here. This was 10 to the minus 6th and 1, 2, 3, 4, 5. Oftentimes you have like one less zero than you expect. So keep that in mind.
Mr. Bergman, you mentioned a couple of times how we always want to have just one number to the left of the decimal whenever we're writing. We sometimes call that good form, at least I do, good form. So if you ever hear us talking about write it in good form, it just means that we want you to shift the decimal place all the way over to there was only one number to the left of it.
And the reason I actually will do that, my old high school chemistry teacher taught me this, is if you've got 0.3, like 0.03, sometimes that it's not easy to see that, and then you just see 0.3. But if you say 0.03, and those really are the same number, I know that. But sometimes you can miss it, all right? And it's hard. Or actually, even worse case, if you've got 0.3, if for some reason your eyeball doesn't see the decimal there, the point, but if you have 0.3, it's going to be easier to spot that when you're writing out numbers. Anyways, so let's first of all talk about multiplication. So what do?
Yeah, whenever you have two exponents and you're multiplying them together, you add the exponents together.
So if I have 3 times 10 to the 6th times 2 times 10 to the 8th, then you would take 3 times 2, so that's 3 times 2, of course, 6 times 10, and then we add the exponent. 6 plus 8 is 14. That's simple. Now, we'll show you how to use these on your calculator if you get lost, because oftentimes you're not going to have nice, pretty numbers where you can do it in your head. All right, what about divide?
Divide is subtract.
So what's the rule? What do? Not add exponents, you
subtract exponents.
Subtract exponents. So let's say I take 6 times 10 to the 14th divided by 2 times 10 to the 8th. 6 divided by 2 is 3. 3 times 10, I'm going to subtract the exponent. 14 minus 8 is 6. Okay? And then what about add and subtract?
This is actually the hardest thing to do because you have to go back to what we just talked about in shifting decimal places. You always have to make the exponents the same. So make exponents the same.
So let's say I have 6 times 10 to the 14th. I'm going to add 3 times 10 to the 15th. And what I need to do is I need to make them the same, right? So what I need to do is, let's say there's 3, I want to make them both, let's say, to the 14th. Or the 15th, I think, right? Yeah. So I'm going to make this the 15th, so I'm going to move this decimal to the left. I'll say 0.6 times 10 to the 15th plus 3 times 10 to the 15th. And I'm just going to add 0.6 and 3, so that becomes 3.6 times 10 to the 15th.
Just remember the rule there, lefty largy, righty reducing.
And honestly, if I were you, I would just do this on your calculator and let it solve that. And you're going to learn how to do these on your calculator using exponents as well, because you're going to be using some big numbers, and then the calculator can solve these problems. But it's going to be hard to understand how to read the calculator. All right, folks, that's all for this video. Any last thoughts?
No, let's try these.
Awesome. We'll see you in class.